Good afternoon, everyone, and welcome to our live session. Thank you for your patience. We are just making sure that enough number attending and admitted. So right now we will start. First of all, let me introduce myself. My name is Ahmed Khairi. I'm a geophysicist in Balayan Petroleum Company in Egypt, Petrobel. I will be the coordinator for today's session. Before we start with our instructor, I would just like to share with you some introductory slides. Uh, so 1 second, please. Yeah. First of all, I would like to thank you for all the support that you have shown to NEUSTRA. NEUSTRA is a new community. It's interested in machine learning applications in geoscience, and not only in geoscience, but in all earth science field, geoscience, petroleum engineering, and even we are interested in applying machine learning in other fields rather than the geoscience. So everyone is welcome to join our community, of course. I would like also to share you with you some uh, good statistics about this event. It was a surprise for us in the community because the reach that we have in Facebook, like 20,000, more than 20,000, more than 600 response, uh, almost 70% of the people, men interested, and 30% women. And with the main interest in the 18 to 24 years old and 25 34 years old. And however, we have also from the younger generations and older generations. So it was a good overview about the interest of our followers in the machine learning session. So finally, I would like to thank our instructor today, Mr. Yohanes Nuwara. He's very supportive to the geoscience community, and especially to all the geoscientists who are interested in machine learning. I really encourage everyone to connect with him in LinkedIn and in GitHub. He's really helpful and supportive, and I personally consider him as a friend. So Johannes, as a quick introduction, he has his Bachelor of Science degree in 2019 from Bandung Institute of Technology, and it seems like that he's a fresh graduate, but really he has a very good career, especially in the mastering his programming skills in Python and MATLAB, in numerical skills. And of course, he has other experience and activities that we shared on the event page on Facebook. So I welcome him to this session, and I leave to him to the word to start the session. So to you, Johannes.
Okay, Ahmed, thank you very much for your introduction. So, first of all, I would like to say thank you for your attendance and your invitation to this NEUSTRA community. I personally, I'm very surprised when you show the statistics earlier. That's a really great achievement for our community. And yeah, as you told earlier that I'm a recent graduate, and the journey that I was into Python is not too long, because it was started from 1 year ago. I took a course, and then different from other people who took the course, I then upgrade my skills, and then I solved some textbooks that right now I maintain some of my works in my GitHub, and the works is mainly in reservoir engineering. And I'm really surprised that this repository is getting really useful for students and for people. And I'm really glad to see kind of contributions to the petroleum community. And today I would like to share my recent work in machine learning in geoscience. And I think that machine learning is a future for all of us. You know, we hear lots of things about machine learning, data analytics, and it was getting really popular in geosciences and in petroleum engineering. You know, lots of people are developing lots of models and and they are getting lots of data from the fields. Or for example, because Ahmed and I are geophysicists, we are gathering seismic data in the field and some logging, for example. Lots of big data there in the field. We can analyze it using machine learning. So I think machine learning is a hype for our community itself. So I think I would like to share my screen right now. And basically, I'm really glad to see the applications of machine learning are getting more and more popular. In the past 2 years and 3 years, I saw lots of trends and in the geoscience itself. And as I know, Ahmed also created a repository in machine learning and paper machine learning, which I considered it is a really good initiative to compile lots of information into a repository. And okay, so Ahmed, I think the host disabled participant screen sharing right now. So it seems that I couldn't share my screen. Ahmed, do you hear me?
Yes, Johannes, I hear you. You have a problem
Yes.
sharing your screen?
Yeah.
Okay.
So I think, yeah, it should be take.
Okay, let's try again like this, Johannes.
Okay, yeah. Yeah, there you go. Thanks, Ahmed.
Yeah.
Okay, so I hope that you have already seen my screen right now, right?
Yeah, it's clear.
Okay,
Yeah.
Okay. So today's talk will be in machine learning for sonic lock prediction. I know machine learning helps in lots of things, like it can classify faces, and it can do things like production optimization. But the most popular use of machine learning is to recover when we don't have a complete data. Or for example, we are gathering a well log data from the field and we don't have a sonic log. We can use machine learning to generate new sonic log. Okay, so today's topic will be machine learning for sonic log prediction, and the case study will be in a field in the full field data set. So first of all, before we are getting to know what machine learning is, or when we start to work in machine learning, we have to differentiate, or we have to know the meaning of some terminologies that we all know in machine learning. Here we have classification and regression. Maybe some of you have already started machine learning, or some of you have been in PhD researching on some data that use machine learning. So basically, machine learning is categorized into two: classification and regression. When we do the classification, it's that we are dealing with, like, we want to classify facies in our log, whether it is sandstone or it is limestone. So that's the job of classification. But in regression, in the case that we don't have a complete data and we want to predict a new data, that's called a regression. And here I want to show you an animation that can help us to understand more about machine learning. So here we have an example of well-log data. As you know that there are lots of logs there, like density, resistivity, gamma ray, and of course the sonic log, and also it can appear as the phases or the formation labels. I took an example for Egypt. There are Belayim and Ruday's formation. They are all information that we can do machine learning with it. And the second data here, as you see, you may notice the difference here. The second data doesn't have the sonic log or the DT log. So here we are dealing with regression because we want to predict a new DT log on our second data. I hope that you understand this analogy. And the way we differentiate this data, we should know what's the difference between training and testing. Okay, so when we are dealing with training data, it means that we have the complete data. Like here in the first table, we have all information, the density up to the sonic log, but in the second data we don't have the DT log. So you can differentiate that the first data is the training data and the second data is the testing data. Why testing data? Because we want to predict in our test data set. And then you may come across also a terminology, for example, supervised and unsupervised. Here we have a supervised learning. What the meaning of supervised learning? So you have all of the information, and you already have some labels there, the formation labels. So this formation label can guide you to learn in this data. So there are information that can guide you in learning the data, but in the unsupervised learning, you don't have a guidance. So the machine learning algorithm will learn by itself. So the algorithm learned by itself. Although unsupervised learning, we don't see like regression, but in supervised learning, we can do both regression and classification. But in unsupervised learning, maybe you will see like k-means clustering or t-SNE. That's only for the classification. So no regression in unsupervised learning. Also, we should know what is the features and the target. And if we see here, we have this kind of data, the density, resistivity, gamma ray, and formation. These are the features. The features are the data that the algorithm will train. And this one, the sonic log, is the target. Why it is called the target? Well, because we want to predict the sonic log. So the target of our prediction is the sonic log. So the features are those 4 logs, and then the target will be only one variable, that is the sonic log. Okay, and then what is the observation? You see here, you can see that there are 4 columns in this data, 5 columns with a target, and we can count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 observations. So each rows is associated by like the observations. So there are 10 observations, and in well-log data, we have like 1,000 of observations per depth. Okay, and then we see here another term like continuous and categorical. In this continuous, like we are dealing with numbers. That's easy definition of continuous. We are dealing with numbers. But when we are dealing with like here we have the formation, like here Belayim and Ruday's, there are 2 formations. We are dealing with categorical data. So these are the continuous data, and the formation is the categorical data. And then we also have this missing data that is called the non-numerical values, or people call it like NaN or none. Okay, so the critical step in machine learning is that we have to handle this missing data. Okay, so the way we are dealing with missing data, we can first, we can impute the data, or we can just delete the observations that don't have data. So later on, we will discuss these two ways. So in this animation, we are imputing new values to fill up the missing data. That is called the imputation of the non-numerical values. And then after this, we are trying to predict the sonic log here. Okay, so after we are doing the prediction, we compare the predicted result with our true or original data here. Okay, so the comparison between these variables is called the accuracy. So you measure the accuracy of your model that you are creating by yourself, and then you evaluate by yourself, is my model is enough to predict my my sonic log. If the accuracy is low, for sure you don't trust your model, so you have to upgrade or improve your model until the accuracy it is hoped that it is never, in fact, it is never 100, but in 90 or 95% accuracy, that's a good model. And after we are having a good model, we are taking the model and then we are predicting with the model on our second data that we don't have the DD. Okay, so earlier we are discussing about the testing data. So here we are predicting with our model in our test data. So the result will be in the DT column. So after we have, so that's the result of our prediction or our regression. Okay, so basically we can decompose our workflow into this kind of flow chart. First of all, we have the data. Of course, we have lots of data. And more data is useful because it can learn the pattern inside the data, and it can give you insight if you have more data. And after you have lots of data here, it is better for us to do what is called by exploration data analysis. Well, if you know what histograms are, or what box plot, that are called the exploratory data analysis. It is using the visualizations to know more about our data. And also we need to know what's the summary statistics, like the average value or the standard deviation of our data. And after we are doing exploratory data analysis, or people just call it EDA, we are doing feature selection and feature engineering. As you might know before, we are already discussing about feature. Some features are appear to be not so important to be included as a prediction. Let's say, for example, first we have density, resistivity, gamma ray information. In our second step, we are evaluating which features here are important for our model. If we see that, for example, gamma ray is not so important for our machine learning, we are eliminating gamma ray. So we are just selecting what's the best features for our model. And also, we can also engineer or create a new feature by ourselves, like we are transforming our data into a new feature so that this new feature can be used for machine learning. Later on, we will discuss it more. And after that, we are normalizing our data and removing some outliers. I have to make a stress on these steps because this is the most critical part of our machine learning. They are not, machine learning is not just an instant time. We are doing machine learning within a day or even a month to make a good model. Okay, so when we are having our data, we have to normalize our data and we have to remove some outliers. Okay, so machine learning can work better if we are having a good data, it means that we are having minimum number of outliers. So we have to do pre-processing before we are doing the real machine learning. And also, after that, we are doing what is called by the train test split. You already know what is training and testing data. It's just like we are separating which one is training and which one is testing data. And then we are doing our first prediction to compare the predicted versus the true DT log, okay, so, the true variable. And if we compare, after we are comparing and we are having accuracy of 95%, for example, we can use this model to predict in our real test data. Okay, so I'd like to explain to you all what data that we will talk about right now. It's the Volve data. Well, Volve field is a field located in North Sea. They are owned by Equinor, and they have been developing, I think, since 2008, and it has been producing for 8 years. And 2 years ago, Equinor, as a company, released their data set for research or for universities to research in this data. And I think this is a really treasure for us, because sometimes we are having difficulty on getting a new data from our field, or we are dealing with confidential data. But with this initiative, we can use this data for our learning instance. So these are the overview of the field. Like if you are going into the Equinor website, or if you want to search for this data set, you can go to Google and then you can search Volve field, and then you will see the access to the database, and then basically you have to download, but it's not so difficult to access the data, because you can access the data by yourselves. And if you are looking into the data, there are lots of wells right there. But here in the study, I just used 5 data. And in this 5 data, 3 of the data have the DT log or the sonic log, while the other 2 wells doesn't have a sonic log. So as you predict earlier, that we have been already discussing which one is the training data and which one is the testing data, we can just like we can guess which one is the training data, which one is the testing data. So here we have well, 1, 3, and 4 have DT log, so that will be our training data because it has a sonic log. And the well, 2 and 5 it does, because it doesn't have a sonic log, so it will be our testing data. Okay, so I hope that you have already understand what is the training data and the testing data, because it's quite critical to know. Here we are seeing the well log of the first well of our training data, and then this one is the other wells. Okay, so here we are seeing the neutron log, like the density log, gamma ray resistivity, the true resistivity, and the photoelectric factor, and the caliper. And what we are going to do now is that we want to, okay, so these are the complete data, right? And this one is the incomplete data, because it doesn't have the DT log. So we want to predict the DT log from these features. There are 1, 2, 3, 4, 5 logs. So we are using these features to predict the sonic log. Okay, that's quite straightforward to think about that. And also this one is the other wells. And we are talking right now the workflow of the machine learning, which is started by the exploratory data analysis. First of all, in EDA we have lots of tools actually, but These 2 or 3 tools are my most favorite EDA tool. The first one is the pair plot. If you are seeing your data, maybe you have already know about what's the difference between univariate and multivariate in our geostatistics 101. And to visualize the data, the distributions of our data, we are using the pair plot, okay? So for example, when we are dealing with univariate distributions, one question that might appear, for example, how is my porosity log distributed? It is Gaussian or it is skewed, left skewed or right skewed? Is it Poisson? So there are lots of questions right there to consider which distributions is our data. And also, you might also want to know the most frequent or how much porosity is the largest concentrated in my log, whether it is high porosity or low porosity, or which, for example, we are handling with really heterogeneous rocks. So it will be more Gaussian because there are lots of variations in the porosity. So that's how it's called the univariate. We are seeing just the distributions on the data, okay? But when we are talking about the multivariate distribution, we want to know, is there any linear correlation between 2 variables? For example, we have a neutron log and density log. Is there any linear correlation between neutron and density? And this is important because we want to predict a new variable from the other variable. So we want to get the correlation between 2 or more variables. So because we are right now talking in Python, there is one library for me that's really important. It's a really important library that is called Seaborn. Maybe some of you here has worked Python lately, and maybe some of you have already familiar with Python, programming with Python. There are lots of libraries in Python, and Seaborn is a statistical library. Like in our programming language, we have rstats. And I want to show you how is the pair plot in our Volve data. So this is the appearance of the pair plot. Maybe some of you have already know about pair plot or the visualizations of pair plots. So this is the pair plots. We see here are the variables, okay? The first is the variables, and the second axis is also the variables. So we are measuring the distributions and the correlation among the data or among the variables here. The first thing that when you are seeing a pair plot, you have to spot interesting things from this figure. Okay, so at least we already we have like 8 or 6 interesting observations from this figure. Okay, so here we know that this one is the neutron log, okay, and we know that the distributions are more skewed. It's not so Gaussian, or it's not normal distribution. It's more skewed here, okay. So and then the another observation that is really interesting is this, okay. So if you guess what happens with these distributions, well, when you are analyzing petrophysics or formation evaluation, maybe some of you are working in formation evaluation, the way you are visualizing the RT or resistivity log is that you are transforming the axis into logarithmic. And because the resistivity here hasn't been already transformed into logarithmic function, it appears a spike distribution. So later on, we will be able to change or to what we call it, to not to modify, but to transform the distribution so that it will look more Gaussian. Because the more Gaussian our data is, the more machine learning works better. And the another observations here, we can see here the outliers, okay? And this one is the outliers, okay? There are lots of outliers here that we have to remove later. And also maybe we can see the positive correlation between the neutron log and the density and the sonic log here, okay? And also another positive correlation between density and photoelectric factor, and also negative correlation between density and the sonic log. And maybe we also have data that have no correlation or less correlation, for example, between caliper and DT. So just from this one figure, you have lots of things to interpret from your data. And from your interpretations, you should be able to design what's our next step after this. Do we have to do data normalization, or we have to do the outliers removal? All starts from the EDA, or the exploratory data analysis. It decides which path that you will go after this, okay? And also, there is another exploration data analysis here. It's called the heat map. Maybe you have already know about correlation, the Pearson's correlation or the Spearman's correlation. The way we visualize these correlations, we can use the heat map, okay? And this tool will tell you which features are not so important for our model. So here we have the heat map of the Volve dataset here. All the variables in one axis and the another axis right here. And in the last row, you will see here are the sonic log row. And each of this block represents the correlation between DT or sonic log with the other variables. Okay, so right here, as you see here, which one is the lowest correlation between DT and the other variables? Which variables having low correlation with DT log? And it's visible that that the photoelectric, sorry, the caliper here doesn't have so much, doesn't have enough good correlation with the DT log. So later on, actually we can phase out, or we can just ignore this feature for our machine learning just because this has low correlation. But it is always advised for you to try first all the features, and you will see if the model that you will create is representative enough to predict your data. If we have low accuracy, we need to phase out this not so important feature. So it is advised for us to include all these features before we decide which features we have to phase out. Okay, so it is quite critical for us to handle some missing data. Maybe you are taking data chem courses or some online courses, and you will see the data are so ideal, right? They have complete data. But in reality, if we are dealing with geoscience data or petroleum engineering data from the field, maybe because there are some surprises in the field, for example, bad weather, or some incoincidences that happen in the field. Okay, maybe we are getting missing data, and how to handle this missing data? There are some techniques, and why we have to care for my data. If I miss my data, why do I have to care? Because machine learning have to can predict if we have a complete data. Okay, But don't worry if you haven't if you don't have a complete data. You can do two ways to fill your machine to fill your missing data. For example, here we have a technique um, to impute, or we just calculate the average or the mean value of our data, and then we just fill all the missing values with those numbers. That's called the imputation. But maybe it takes longer than we just delete all the rows that has non-numerical values or missing data. But if you are handling with, like, for example, Veloc data, because the logging tool record each depth, okay, so it appears like 1,000 of data, or even higher than that. You don't have to be worried if you just delete some rows, because maybe you have about 10% of your data phased out. So you have, for example, 500 data or even more. So if you have a big data set, you don't have to be worried if you just delete all the observations that have a missing data. And exactly in our Volve data set, there are lots of missing data. And we can just delete all the observations without any imputation, because these are really big data sets. And the way we can visualize the missing data, we can use also the EDA tool. Actually, this one is not widely used. I created this for myself. So actually, the way we are building something in Python is really simple. We can just use 3 libraries, for example, NumPy, Matplotlib, or Pandas. So in most courses that I give, I encourage all the participants to master these 3 libraries to create lots of things. I saw lots of people out there are using lots of libraries like Neo libraries, but in fact we can create our own tool with just 3 libraries. And you see here is a visualization of the missing data here. Actually, Volve field is only one field of the North Sea fields. There are lots of fields in the North Sea, and here we have like 500 wells in the North Sea. And if you are counting all the missing data one by one, it is wasting our time, right? So if we create a tool that can visualize more than 1 wells, okay, that will be useful for us. Okay, and here we can analyze how much data are missing in each these wells. There are 25 wells, okay, so I just display 25 out of 200 wells, and you can see here is the missing data, okay. And the importance of seeing this you have already known, because machine learning can only receive if our data is complete. So we can just delete these observations that are missing here. Okay, so maybe, for example, in case here in this well 8.1, we have 20% of all data that are missing. So if we are having like only 20% of 10%, we can just phase out. But here, because we have 200 wells, I think we can just delete these observations, because we have a really big data set. So we don't have to be worried if we just delete some observations. But if you have only like 2 wells, or even only 1 well, and about 50 or 40% of the data is missing, it is not advised to delete all these rows. All you have to do is you have to impute there are several imputation techniques. Actually, it's not only to impute with average value. You can use all methods. You can just browse in the internet all imputation methods to complete the missing data. And it's really important if you have those kind of condition, you just have two wells in your field, and then most of these wells are missing. So you have to do imputation without deleting these rows. But here, because we are having big data set, we can just delete it. Okay. So another important, actually this is not so important because this is the optional workflow. We can transform our feature and create a new feature. That's really cool, right? We can create our own feature. For example, earlier we know that caliper and DT log is having low correlation. We can transform this caliper so that the correlation between the new transformed caliper log with the DT log improves. For example, we can do some mathematical functions. For example, you can transform it into logarithmic function, or maybe you can take the exponent of the data, or you can take the square root of the data. So that, and then after that, you just measure the correlation. And if you have a correlation, for example, 0.6, you can just use your feature. So feature engineering is just how we change our data. And as we remember that in our resistivity data, we have the spike distributions. So let me show you once again here, the B, okay? Here we have a spike distributions, and we don't want our resistivity data to look like this, okay? And the way we can do is to do feature engineering. And the way we are doing feature engineering in resistivity is really simple. Earlier I talked about formation evaluation or petrophysics. Usually we are visualizing, or not usually, but always we are visualizing resistivity log into a logarithmic axis. So in this case, we can also take the logarithmic of the resistivity so that it can be a new feature, or to transform the RT into logarithmic of RT. And if we are showing once again the pair plot here, can you see the difference? The resistivity here. So this one is the resistivity, right? The resistivity rows. This is resistivity and with correlation with the other variables. And this one is the distributions. Here you can see that the distributions looks more Gaussian, right? So it doesn't any longer look spiky because we have already transformed the resistivity log into the logarithmic, okay? So that's really important on how we can do feature engineering to repair our log so that it can have a nicer distribution. And another critical step is that we need to do transformation of our data. What do we mean of transforming our data? Like this, we have the distributions that look not so Gaussian. It's skewed distributions. Here we also have like not so good distributions, not so Gaussian here also. And this one is skewed. And the way we do the transformation, the objective is to transform the distribution so that it will look more Gaussian. There are lots of techniques, but the most fundamental methods of data transformation is the standardization and the normalization. The way you standardize the data, you can use the standard deviation and the mean value of the data, okay? And then you just transform the data using these two values. And another technique is called the normalization. The way it's done is just you have this data, and then you compute the maximum value and the minimum value, okay, and then you subtract the data with the minimum value over the maximum value minus the minimum value of the data. That's called the normalization. Why it's called the normalization? Because it will transform your data from 0 to 1. And then also we also have other methods, for example, power transform or regularization. And here we have all of these methods in scikit-learn. Scikit-learn is a Python library for machine learning, and all of these methods you can find in scikit-learn. And it is really advised for us to compare which transformation method is the best. Okay, and in this case, what I found from this Volve data set, the power transform here, the power transform with the Geoscience method is the best method to normalize our data. So after this, we'll see the magic. Boom, we have this distributions, okay? And as you see here, we can focus in this box, okay? This box. If we compare with so if we compare with this distributions, let me show you here, okay? So this is not so Gaussian, right? But after normalization, it is more Gaussian here, okay? So actually it is not so visible, but you can compare, right? This is the first method that is called the standardization, but this is not the best method. The best method is this Geoscience method, the power transform method. As you can see here, you can compare by yourself which one is more Gaussian here. Okay, so in the first box here, this is the method, the power transform method, and this one is the standardization method. So you can decide which normalization method is the best or is better than the other methods. Here also we have something more spiky here, but if we are using this method, you can see this looks more Gaussian. Also here, the third box, we have a more Gaussian looks. So after we are comparing these methods, we can see that this method works very good for normalizing our data. So we are using this method. And after this, we also know there are outliers that we identify from this data. This one is the outliers, okay? So the next step, as you guess, you have to remove the outliers. And the way we see the outliers in our data, we can use what is called by the box plot. So for example, here, we have, in this box plots, this is before the outlier removal. We have this kind of outliers here. You can identify this one is the outliers of our data. And there are lots of methods to remove our outliers. For example, we can use isolation forest, but the best method that we found here is using the one class support vector machine. So there are isolation forest, minimum covariance, local outlier factor, and one class SVM, and we compare which one is the best using the box plot. So after we are doing the outlier removal, we can compare which method is the best by seeing the statistics here. We see we can compare how much number of points removed, number of outlier points are removed after each method. You can see here, of course, the less outliers removed are better because we don't want to lose our data. So we just want to remove some small of numbers of our outliers. So as you see here, the last or the least outliers to be removed is using the standard deviation, okay, because this is the highest number of points. And also here, the minimum covariance and the one class SVM. As we already have 3 candidates, we need to decide which one is the best by using the box plot. And here we see the comparison between lots of methods here. For example, we are seeing here the minimum covariance and the one class SVM. And we see that this one class SVM remove the least outliers from our data. And we can see this is more cleaner. This is cleaner than the other method. Okay, so just from this representation, actually, this is my tool. So actually, the way we are doing machine learning, we have to imagine one tool that can help us to know whether our method is already correct or not. So this kind of representation is what I created. So maybe some people have already also created some kinds of this box plots, but I created this kind of representation to help me interpret which outlier removal method is the best. So here we have this one class SVM as the winner, okay? And if we apply this outlier removal, okay, we can see the difference here, right? We see less outliers here, okay? So the outliers have been removed here, okay? So this is the cleaner version of our data. Actually, it doesn't mean that we lose the information from our data because we are changing too much in our data. It is not that way. We are just transforming our data, not changing the information in our data. So so the data after the normalization or after the removing outliers or after feature engineering and before, it's still the same. There are no information loss, only the outliers removed. But overall, we don't lose information in it. Even we don't lose the correlation between one variable and the another variable. All those variables are still those variables. And after this step, we already have the data, okay? This is our data. So what is called the data for machine learning? The data that is after pre-processing, we already have a good data. So that's called data for machine learning. If we have like raw data, it is not well prepared for machine learning. So after this, we are just starting our machine learning workflow. Here, actually, you can browse in the internet the definition of the machine learning models. So because we are doing regressions, there are some regressors. For example, the simplest one is the linear regression, and another one is a decision tree, random forest, and support vector machine, and also KNN and gradient boosting. This is generally the definitions of each method. Okay, so the simplest one is linear regression. You just recover the linear correlation. You assume that all data is linearly correlated. You use a linear regression. And also maybe we can use the decision tree. It works like we are segmenting the data in zones. So the decision space in our data is segments. So that's called the decision tree. And also the random forest, it works like like the decision tree, but it improves the decision tree. And also we are also using the KNN. So basically KNN is we are setting a new, that is what is called Euclidean distance. The distance between one point to another point, which is, we can cluster this point, that is called the KNN, and also the support vector machine and the gradient boosting. Actually, this method is not so difficult. You can just understand the meaning of each method, and it's not so horrible to understand one of these regressors. And in this study, I just use these 6 regressors, and I want to find which regressors is the best. Okay, and the first step before you are doing the real prediction, you have to compare the predicted result with the true variables. You can so for the training data, you just merge all the wells. Okay, so this training data have 3 wells, and for the test data, you have the individual wells. Why we are doing like this? Maybe you are asking. So it is clear that we want to compare first before we are predicting in our data that has that don't have the DD log. We just want to compare the predicted result and the true DT log. I hope you understand this this step. So the way we are doing this this way, we are merging the data, the training data, and then we just fit the data with the regressors, okay? And with the model that we have already fitting in with the data, then we predict with the model, with the data itself. I think you maybe it's quite complicated for you, but the way we are doing like this is just to compare the predicted result and the true DT result, okay? And after we are predicting these 2 result, if the accuracy, so we are measuring here what is called as the metric. There are 2 metrics that we know. The first is the R-squared error and the root mean square error, or the RMSE. After we are predicting in our test data, we just measure the accuracy, the RMSE and the R-squared. Okay, so after we are having this metric, we can decide which one is better and which model is representative. So for example, here there are numbers here. These are the metric of each regressors here. So because we have 3 data that has sonic log, we have here the accuracy of each method here, and you can see that the best method that has the highest accuracy is the gradient boosting. Okay, right here is 0.9, 0.9, and 0.9 here. Okay, so yeah, I think there is better here decision tree, but I find that boosting is a good model to predict data or to be used as a regressors here. And after we are seeing this this metric, we can compare the predicted result and the true sonic log result here. Okay, so you can compare the closeness from these 2 results, right? So this is the true, and this is the predicted, and this is using the linear regression method. Actually, this is pretty good. This is good enough to represent this this DT log. And also, this is the another method using random forest here. Okay, so just see how close they are, the predicted and the true. So I think we we can call this magic or like a wizard. But the way machine learning works is that it just learns from the data without using like using complicated stuff. It just learned the data from the correlation. Earlier, we already talked about the linear correlation or the Gaussian distribution. So the machine learning is looking inside this pattern inside the data. And then after they are looking the pattern, they retrieve the information from the data, they build a model, and then they predict or apply this model to the data. So machine learning is not a magic. It just look inside the data, and it looks the statistics of the data, and then it use the model to predict a new result. And this one is the support vector machine, and this one is the decision tree. Oh, I see here. This is not so good, right? Because it's not so close here. So we don't think that CART or a CART is classification and regression tree, or called a decision tree. So we don't think that from this figure, decision tree is good enough to predict our data. And here is the gradient boosting. This is the most loved method for machine learning enthusiasts. I saw lots of people are joining Kaggle and they are winning the competitions there. They are using the gradient boosting. Maybe why the gradient boosting is really powerful, because by the definition, if we go back into our definition here, gradient boosting is a general ensemble method that creates a strong regressors from a number of weak regressors, specifically the decision tree. So gradient boosting is a model that improves the weaker regressors. Here we have we already see the decision tree here. Okay, so it's not so good model. And the GB, or the gradient boosting, it works to improve from these weak regressors. This is really brilliant because at the discovery of machine learning, people are creating lots of methods, and they are creating lots of creative methods. And the way gradient boosting works is just by like improving other weak regressors here. So that's why gradient boosting is very powerful, because it creates an ensemble or compilation of the weak regressors into a more stronger model. And the last one we see here is the KNN. If we compare here, okay, so this one, which one is better? Of course, the gradient boosting here. We see how the predicted follows the trend from the true sonic log, but here it is more spikier or more noisier. Okay, so just from this comparison, you already know which model that you want that we will use. Okay, so in this case we are using the gradient boosting. But hey, we can see here some parts of these logs are not so correlated so better. Okay, so we can actually improve our model that is called by the hyperparameter tuning. So okay, so which one is the best? We can see that the highest R squared and the RMSE is 0.20 and 0.95, and we can improve this gradient boosting by doing a hyperparameter tuning. So hyperparameter tuning, if you already know about what is called by optimization, maybe you are working with genetic algorithm or simulated annealing. They are the optimization methods. So hyperparameter tuning is an optimization method. What's the meaning of optimization method? So the gradient boosting or regressors, they have default parameters that is called by hyperparameters. And when we do earlier this prediction, we are using the default hyperparameters. So let's say we are using the scikit-learn and we are doing the gradient boosting without defining any hyperparameters. It just turn the default hyperparameters. But the way we are doing hyperparameter tuning, we want to search which combination of hyperparameter is the best, so to improve the accuracy and the performance of our model. So here, for example, in GB, we have, actually there are 10 or 5 hyperparameters in gradient boosting, but 2 of them is the number of estimators and the maximum depth. So the default number is 103. And after hyperparameter tuning, we can see the most optimum estimators and maximum depth to improve our model. So there are lots of methods to do hyperparameter tuning that is called the Bayesian optimization, grid search, and the randomized CV or cross validation. And from the fastest method is the Bayesian optimization. And here we are using the grid search CV to improve the hyperparameters. So after hyperparameter tuning, we get the best hyperparameters. The number of estimators as 1,000 and 100. So the default is 103, and after hyperparameter tuning, we are knowing that the number of estimators is 1,000. And you can see here the 2 figures here, okay? So you can compare the performance before hyperparameter tuning and after hyperparameter tuning. There are lots of improvements here, okay? So from 0.95 to 0.98, and also the root mean square is decreasing. So hyperparameter tuning is really powerful to improve our model. And actually we can do more than one hyperparameter tuning, but I can say that hyperparameter tuning is the most expensive step in the machine learning workflow. One, because hyperparameter tuning takes more time to execute, and 2, hyperparameter tuning is really computationally expensive. If we are using the grid search or the randomized CV or cross validation, because we are constrained with not so big memory in our laptop or our computer, we spend lots of time to search for these hyperparameters. Just to search for these hyperparameters, it takes a long time. In my case, when I was searching for the hyperparameters, it for about 7 minutes. So actually 7 minutes is not so long for you, but in terms of computational language, 7 minutes is too long. So I think that hyperparameter tuning is really powerful, but it takes more time. But it is really worth it to improve your model here. And if we apply the tune model, okay, here, so after we are having our model, we are predicting in our real data set here. So at first we don't have the DT log, and now we are producing the new sonic log here. Okay, so this is the only one of the wells here. Okay, so here you can see that that the predicted log here, you can see it follows some trends from the features. This one is the features, as you remember. This one is the features, and it predicts nicely the new sonic log. So machine learning is really wonderful. It can predict a new variable. If we don't have a complete data, we can produce our own data using machine learning. But one most important thing is that we have to validate our results with the real petrophysicist, or with the real workflow that we are developing when we are doing formation evaluation. For example, machine learning cannot detect whether it is rough zones or um, an indication of borehole invasion, or it cannot detect which one is the hydrocarbon zone or the water zone. So um, in the real machine learning workflow, we are handling with this kind of information before we are doing machine learning. So we make sure that before machine learning, we know our own data set. So it is important to get to know our data first before we are doing machine learning. As to say that if we don't know anything about our data and we are just directly applying machine learning to our data, we don't know exactly what is happening in our data. For example, we have a rough zones that the machine learning cannot detect it. After the prediction result will wrongly predict those zones. So it is really important for us to do pre-processing before we are doing the machine learning. So I think that's the workflow. We are already talking about the workflow. And now I would like to show a short demo of programming machine learning. So here, I think you can also access this notebook. I will share the link after this. But you can see in my GitHub. So maybe some of you have already familiar with GitHub. GitHub is a really powerful tool, powerful storage to share your codes or to share the data or to store your data. And I have stored this short demo in my repository. So I think I will open the notebook. So here is my notebook here. So I think I can share right now. Okay, so oops. Okay, so maybe I can show you the link for machine learning. So I will copy this, and then you can see the notebook here. So okay, so here I have already prepared the notebook for our today's talk here. So you can see the notebook here. You just click here, okay, and then you can actually it takes a long time to load this notebook. If you see so actually okay, so actually something went wrong because it's really a big notebook. But if you are opening this this link, you will see a notebook like this one, okay? So here is a short demo of using the machine learning for the sonic log prediction. And this, so first of all, this is the Google Colab. So it is just like another IDE like PyCharm or Anaconda. Only Google Colab is an IDE that runs in the cloud. Okay, so we are just using the internet to use the Google Colab. So here we are starting everything as usual from NumPy. Okay, so these three libraries, you might have been familiar with these three libraries. Okay, so this is the GitHub repository that all the data and all the workflows are stored here. So if you want to see the data here, so this is the data. This is the 5 well logs. And we are retrieving this data into our Google Colab. So the advantage of using Google Colab is that we can stream the data directly from the website or from the GitHub without even downloading the data into our computer. So we are training our data. Okay, so we are training the data first. So it's in CSV file. this is the data, okay? So this is the data, this is the training data. We have features here, neutron density, gamma ray, RTPF, etc. And also, as we already discussed earlier about the EDA or the pair plots. So this one is the pair plots, okay? So we are using Seaborn, okay, so to produce these pair plots. So this one is the pair plot between all of these variables, okay? And then we also plot the heat map or the correlation from what we have already discussed before. We can see which features are correlated with the other features here. So here is the heat map, okay? And this one is the DD, the sonic lock. And also we do the normalization, okay? So here we use the scikit-learn, okay? And the method is a power transformer here. Actually, you can also use the standard scaler. So there are lots of methods here in the pre-processing module. And after doing the normalization, we are having our new data. So here, you look into the data here, it is no longer this these numbers, right? So the original data is here, it is this one, and after normalization, it is already transformed, okay? So it is no longer the original neutron, it's already transformed into new sets of numbers. And after that, we also remove the outliers. We use the method what is called as the one class SVM. And also, after this, we have already removing outliers. We are now visualizing the pair plots of this one. Okay, so this is as you see here, you see lots of outliers here. Okay, so this one is the outliers of the data, and after the normalization and the removing outliers, you will see they are cleaner. So the most important thing is that we have to compare which method is the best to remove outliers. So to produce this kind of clean data, I took about 4 hours to identify which method is the best. So this one is the most critical step before we are doing the machine learning itself here. Okay, and after that we load the test data. So you can see here the test data as we have, as per our definition earlier. The test data is the data that doesn't have the sonic lock. And also we also define the features. This one is the features, and this one is the target. Okay, and also after this we are defining the training data and the testing data. Now we are ready to predict our to use the machine learning. So here, this is the method that we are using earlier, the gradient boosting regressor. Okay, and as we have already mentioned, what is the hyperparameters? This one is the hyperparameters. The default one, for example, this one is the hyperparameters after the hyperparameter tuning. First, we are doing something like this without defining the hyperparameters. So in our earlier slide, we are doing our first attempt. So we didn't define hyperparameters, so it returns as default. But after hyperparameter tuning, so as you can see here, this one is the hyperparameters of the gradient boosting. There are lots of hyperparameters that we can see here, and two of the hyperparameters is the maximum DN estimators, okay, and the max depth. Okay. And the hyperparameters, after the hyperparameter tuning, we can see this. Okay, so this one is the hyperparameters, and then we feed the data, we feed the model into our data, and then we normalize the testing data. And this is important. If we normalize our training data, we also have to normalize our testing data. And then we are predicting we are predicting with the model, and then after this we are doing the prediction, and this is the result of the prediction. So so yeah, this is the predicted result of the DD. And after this, you can visualize something like we already have before. So okay, I think so yeah, this one. Okay, so you can produce this thing. Okay, you combine finally you combine the predicted result with your original data. Okay, so I think we are reaching the end of our discussion right now. So the conclusion is that using the machine learning, we can predict if we have incomplete data, we can predict or we can produce our own data using machine learning. And here we see that the gradient boosting is a good method to do the regression, but it's not always the case that gradient boosting is the best model. We have to compare, like we did before. We compare which one is the best by comparing the predicted and the true result. And after that, we are doing the hyperparameter tuning to tune up our model. And I would like to say that machine learning is a really good opportunity for us to practice. And we have lots of opportunities to use machine learning in other applications. For example, in the North Sea, there are lots of wells. Like earlier, we see 200 of wells, and some data in the North Sea doesn't have facies labels. So actually, we can use this. We can use machine learning to learn from this 200 wells, and then it will predict the facies of the wells that don't have the facies. So there are lots of ideas that we can come up with when we are dealing with machine learning in geosciences. And because we are now talking about the machine learning in geosciences, I think that the machine learning itself is not only bound to just regression or classification, facies classification or prediction of DT log. There are lots of applications that we can apply machine learning in other applications. Like if you are from petroleum engineering, you know about history matching or reservoir simulation. You can use the machine learning to do the history matching, and then you can combine with a reservoir simulator. And there are lots of as Ahmed also geophysicist, and I'm also geophysicist, we are dealing with seismic data. If you are browsing in the websites right now, there are lots of applications of machine learning for fault identification or fault interpretation. And also, for example, to classify the facies in the seismic section. Actually, in these slides, I don't include the resources, but maybe if you want to discuss with me more, I can provide those resources. Like I constantly working in machine learning, although actually machine learning is not my main domain. My main domain is numerical computing, but right now I'm exploring the North Sea with the machine learning, and I'm searching for any possibility that can bring machine learning to these North Sea models. So I think maybe if you are interested to keep updated with the project, you can follow my Volve machine learning, and in that repository, in the coming months, I think I want to do some other machine learning exploration to do some facies classification in the North Sea models. And my big ambition is actually to train these 200 wells So this, so let me cover it for a short time here. We have like 200 wells here. So these 200 wells have facious labels, but some of them doesn't have facious labels. So if it's a good opportunity to train all of these wells, so that in some wells that don't have the facious labels, we can predict the facious in that wells. So I think if you are following my project there, I will start working on those works, and I hope that it can shed a new light on the North Sea. And so, of course, if you want to discuss with me more, I can be reached in LinkedIn, or if you want to email me. This is my contact here. So anytime you want to discuss some projects, or you want to get some advice on how to start or how to pitch ideas on doing machine learning in geoscience, you can discuss it with me. So I think that's all my my demonstration and my presentation, and I hope that this can shed a light for you, to inspire you to learn about machine learning and start digging more in opportunities to use machine learning for your workflow. So I think, thank you for your attendance. I think it's time to take some questions from the participants here. So
thank you so much, Yohanes. I appreciate your time and your presentation. We actually have a few questions. The first one is, feature engineering is the same as data cleaning?
well, feature engineering it's not the same thing. When we are talking about data cleaning, or data cleaning is when we are dealing with the missing data. We just clean the data, so we just clean any observations that have a missing data. But in feature engineering, we are not dealing with those kind of observations. In feature engineering, we transform the feature. For example, we have a well log, and it contains the neutron porosity or density or gamma ray. We are just transforming these variables into a new variable. But in data cleansing, we just delete some observations that have a missing data. So data cleaning is a strategy of dealing with missing data, but in feature engineering, feature engineering or feature selection, we are just selecting which feature is the best for our model. So that's a difference between data cleaning and feature engineering. Actually, feature engineering is a new thing. Some people are designing lots of features right there. For example, we can create features from coordinates of the wells to better predict our facies. So there are lots of people out there experimenting with new features. So they are creating new features. That's the most important of, that's the most interesting thing of machine learning. We can create our own features, our new features, so that it can improve our prediction. So that's called the feature engineering. It's a new thing, but it's really interesting to know and to try when we are dealing with machine learning.
Okay, thank you, Yohanes. Another one is, how can we check that removing outliers didn't remove valuable data?
Sorry?
How can we check that removing outliers didn't remove valuable data?
Oh, that's a good question. What I can say that the most important parameter of any data is the summary statistics. For example, the mean value or the standard deviation. That's the most important information from our data. But when we're removing these outliers, we have to ensure that our mean value and our standard deviation is not changing too much. So, okay, so I think I can show you the example here. Okay, so I want to back to my screen here. Okay, so here you can see from the box plots here, okay. Okay, so from the box plots, okay, so here, okay, so when we see this figure, is that you can see the box plots here, right? So the green line here represents the mean value, and this one is the standard deviation. And if we see here the box plot after outlier removal and before outlier removal, it stays relatively the same. So it indicates that this method of removal, of outlier removal is good. But if you see here in the isolation forest here, okay, so we see that the mean value is changing after the removal outliers. So it indicates that isolation forest is not so good to remove outliers because we have already lost, we already lost the information from our data. But if we are seeing this result, I think, or lots of people think that we don't miss any important information from our data because our data is still concentrated in the same value of mean and standard deviation. So once again, I want to stress that comparing methods is the most important thing to do when we are dealing with machine learning. For example, here in outlier removal, we have to ensure most of the time that we don't change any information, any important information of our data. And of course, when we are changing some parameter, some data, or we just deleting some data, we will change the data. But if we can keep the mean value or the standard deviation, we don't miss most of our data. So I think that's the answer for your questions, and that's really interesting because it's the most important issue in machine learning. We don't want to miss some information from our data, so that we have to ensure that our model is the most representative for machine learning. I think I have answered your question.
Yeah, absolutely, Johannes, thank you. Another one is, did you try to do dynasty predictions instead of sonic? And if yes, do you have a preferred algorithm?
Oh, okay. That's a really good notion. Okay, so actually in the Volve data set, the elastic and the DTS, or the shear sonic lock, in some depths has some missing DTS or missing lock. So yeah, sure, we can use the machine learning to impute this, or to fill this missing data from the sonic lock. So the idea behind this is just the same. We just use the regressors to predict this data, and then we predict the sonic lock, or the shear sonic lock, or the DTS. So we produce a new sonic lock. So it's not so different with the DT lock. It's the method still is the same, but the difference is that when we are dealing with different cases, our data pre-processing method or removal outlier method will be also different. So I think that's also another opportunity of using the Volve data to predict the sonic S-lock, and that's what I'm doing right now. So to predict this sonic S-lock to complete all the incomplete information in the lock.
Okay, Johannes. Another question is, what is train test split in machine learning?
Okay, so actually, when we are doing the machine learning, um, train task split is just splitting the data into some training data and testing data. So, for example, we have 1,000 data. We just split the data 70% for training and 70% for testing. And for this combination, we use the 70% of our data as the training data to predict the testing data. And actually in this presentation, I haven't mentioned something about the validation. Validation is the another method to, to, um, to ensure that the model works better. So train test split is by randomly separating the train and the train and the test data. So for example, the 70% randomly chosen for the training data and 30% for the training data. And with this training data, we predict into the test data. There are lots of methods to do a train test split. We can do randomly, and also we can do the train test split by splitting with respect to the wells. For example, we have 5 wells. We can use, for example, 3 wells for training and 2 wells for testing, or 4 wells for training and 1 well for training. So maybe if you get more, 10, or for example, in this case, 200 in the North Sea, you can generate like 100 data for training, and the rest is for the testing data. So the most important thing is that when you get lots of data, more data, it works better, because you can split the data into train and task split, and you don't have to be worried if you split this data into train and task split, you just miss some of this data.
Okay, Yohanes, we have another question from Khalid. Would it be better to do outliers removal first before doing normalization? Imagining that we have a gamma ray contains high value, like 1000. After normalization, most of the values will be very low.
That's a really good. That's a really good question. So yeah, we can do so actually, but so let me put in this way: if we do the outliers removal before the data normalization, before normalization we have already missed our data. So actually that's not so good, because we just miss our data and then we just do the normalization. So it is not so meaningful. So if we do the normalization first, we do the normalization, we just normalize the data. Automatically after normalization, some outliers also will be removed. If we see in my previous slide, I'm showing you the data after normalization. Some outliers before normalizations have been automatically removed by itself without missing any data. So maybe before normalization, we have 1,000 of data, and after normalization, because it doesn't miss any data, so it stays 1,000 data, but the outliers itself has been reduced by itself. So and then we just get some little number of outliers, we can just remove it. So if we do the outlier removal first, and then we just lost our data, and then we do the normalization. So it's like we are normalizing some of the data that's already removed. So I think they both can do which one is the first. But for me, preferably I prefer to do normalization first, because by normalization itself, it can reduce the outliers, and then after that, we just remove the outliers after the normalization.
Okay, Johannes, thank you for the explanation. We have two other questions. The first one concerning hyperparameters tuning. Could we run random grid search as a first guess, then run grid search to minimize running time?
Okay, so actually the way we are doing hyperparameter tuning is that we are just choosing which method that we want to use. So there are three ways that I have already we have already mentioned before: the grid search, randomization, the randomized, and the Bayesian optimization. Basically, the fastest method is the Bayesian optimization, but of course, when something gets faster or takes less time, some hyperparameters are not so optimized. So it's not about how to choose which one is the first grid search first and then Bayesian optimization first. The way we can do is that we can do all of them. We can compare which one is the fastest. For example, in this case, the grid search is not the fastest, but it gives us the most preferred combination of the hyperparameters. So the grid search is working by gridding the search space, and then it randomly search until it hits the maximum value of or the maximum or the objective function. It hits the maximum, so it tells us what's the best parameter that we can use. But the Bayesian optimization, it works like it's more stochastic. Okay, so more stochastic, like from jumping from one side to the another side. So sometimes it is faster, but it doesn't hit the maximum or the global maximum of the objective function. So I prefer to use the grid search because it's not so long as the randomized, but it always tells you the most objective, the most optimum hyperparameters that we can use.
Okay, and so our final question, if we don't have another one while asking, do all the log curves in the training data set has to be at the same depth range? For example, from 1000 to 3000, or some of them can have different depth intervals, like gamma ray from 1000 to 3000 and resistivity from 2000 to 3000 and so on?
Yeah, that's a good question. So in machine learning, you have to equalize all the data. So for example, in the real log data, maybe gamma ray and density log, some zones are not recorded. So before we are doing machine learning, we have to equalize the depths. Thank you for bringing those notions. So we have to make sure that each log in our well logs have the same size. So for example, if we have a DT log, they have more DT log than the gamma ray log, you have to adjust the density log into the gamma ray size. So you can eliminate the depth that is not recorded so that all the logs will have the same size. So I think I show this process in my another notebook. You can see the I think I can post my link here so that everyone can see. So I saw here the link that where you can go inside, and you will see there is a notebook. There's the complete notebook that explains this process. So originally the Volve dataset is some depths are not recorded. So in the notebook I show that we can select this the log so that all the logs have the same size of have the same size. So it's important to look into the data. If we have the depth that is not recorded, we have to delete it so that all features always have the same size.
Okay, honey, thank you. We got another question. This will be the last one. So
Actually, that gets more interested after the presentation.
yeah, that's really yeah. Okay, so at least how many variables must we have trains to test one variable?
My simple answer is as much as possible. So if you have lots of variables, like 10 variables, it gets better. But one thing that I always stress is that no matter you have lots of variables, for example, you have like 20 features, maybe some other logs, for example, I can think of the bulk density correction, okay, or maybe what's the other logs that I can think of now? I think the facial or the water saturation or or in the resistivity itself, they have true resistivity, deep resistivity, medium resistivity. So there are lots of logs, and the most important thing is that we have to look at the heat map. Once again, look at the heat map. After the heat map, we can select which features are not so important and important for predicting the new variable. So in any case, we have 20 logs, it's better. But if 10 logs have not so important features, we can just get rid of them, and we have 10 features. That's fine, because we have, for example, we have only 5 or 6 features, but it's highly correlated. It will support the variable that we will predict. So I think the most important thing is that if we have lots of data, we have to look which feature is the most important for the prediction. If we have 10 features, that's good, but we have to look more once again on the features from the heat map or from the correlation or from the EDA tool that you use. Any EDA tool, you decide which feature is the most important for the prediction. Without those features, the machine learning will get better, and the accuracy will get better as the features are more relevant to the prediction model.
Okay, Johannes, thank you so much for this discussion.
Thank you very much. Yeah.
It was very fruitful, and thank you for all the participants for their questions. I would really like to thank you, Johannes, for your time and for the long time that we arranged it together for this session. Also, I would like to thank Iman Ahmed and Abdurrahman Mukhtar. They are the hidden soldiers behind this event. They helped me a lot. And finally, I would like to announce that very soon that we will announce for call for volunteers for the community. So everyone is welcome to join. And we are planning to do many sessions and curriculum for the people who are interested in machine learning. We want to simulate the competitions held by the international companies and organizations like SAG. So we hope that we will really help the people who are interested in machine learning and geoscience. So finally, again, thank you, Johannes. Thank you for your time, for your presentation. And I hope everyone got a really useful presentation today.
Thank you, Ahmed, for arranging this session. It is a really insightful session, and thank you all for joining. I hope that you can learn something from the machine learning, and I hope that there will be lots of researches from you in machine learning and geosciences. So I hope for the best for all of you. And Ahmed, thank you very much for inviting me to give a talk. I really appreciate it. I hope that that the community um, will reach more people enthusiasts in machine learning and in artificial intelligence, because we are already in this era right now. So thank you all for joining. I hope you stay safe all. And if we have another opportunity that we can meet some other day, I would really appreciate to discuss more with you. So thank you, Ahmed, for the session.
Thank you, Johannes. Of course, we
Thank
will
you.
have another presentations and another cooperation. Thank you so much, and thank you all for attending, and see you soon, inshallah, in another session. Thank you all.
Thank you all.
Goodbye.
Thank you, Ahmed. Thank you.
Goodbye.
Stay
Bye,
safe all.
Johannes. Stay
Bye.
safe.
Bye.
Bye.